Then Abhishek Gupta, he's a assistant professor at University of Washington, working on the intersection of reinforcement learning and robotics, focused on human learning, exploration, and generalization. It's going to be talking about some really cool ideas with unsupervised RL and generalized occupancy.
Yeah, camera's good.
Is the camera showing?
I think so. Oh no, turn back off.
I guess it doesn't matter.
There's two of me now. Okay, great. All right. Hi everyone. My name is Abhishek. And today I'm going to be talking about models without models. I had a longer, more informative title, but then I saw Jonathan's title and made me shorten it. And so hopefully we can unpack this and this won't be a mystery. So I'm largely a roboticist and sometimes I do RL. And so when I think of our RL agents, they need to generalize because I'm extremely lazy and I don't want to keep collecting data. And so if I drop a robot into an environment, I don't want it to just do one thing. Like we did a bunch of real world RL, it takes 20 hours for one problem. If I want to do another problem, I have to do it again. That's a huge pain, right? So I really wanted to be able to do things like open my microwave, stack my dishes, use my cutlery, and so on, right? And so I want the same agent to be able to do lots of different things. And I don't want it to just be able to do K different things. I want it to be able to acquire new behaviors quickly, right? And so lots of times in RL, we think about just optimizing a particular problem, but I think we need to think about generalization, and that's kind of the point of this workshop, right? And so when I think of an RL practitioner today, let's say you want to solve these kinds of problems, how would you do it? So you'd start by saying I want to do something like open the microwave. I'd define a reward function. I'd go into Mujoko, hack a bunch of stuff. I'd run my beautiful RL algorithm. I'd get a policy. I'd declare a victory, and then I am now asked to stack the dishes, and I would do the same process again. And I do the same process again, right? So the problem is that for every new task that we kind of define, we often need new exploration and, more importantly, the provision of new reward labels, right? So either someone goes in and programs a new reward function, and that's a pain, or someone sits and labels these rewards. And if I have to do this over and over and over for every problem, it just becomes impractical, right? And so we're not the first field to face this problem. And so computer vision had this problem maybe 10 years ago, where they would say, okay, I want to solve segmentation, so I'm going to collect a data set for segmentation. I'm going to, let's say I collect MS Coco, I label a bunch of segmentations, I trained a segmentation model, and now Jitendra Malik says I have to do recognition. And so now I'm going to do recognition, I collect ImageNet, I label a bunch of stuff, and I train a recognition model, and I do the same thing for detection, right? So I do the same thing over and over and over. And back sometime in like the mid-2010s, they decided that you want to switch to a different paradigm where you mine a large unsupervised data set, right? So you just go on the web, mine a large unsupervised data set, no labels of supervision like segmentation or detection or recognition. You just have a large unsupervised data set. You run it through something like contrastive learning, right? So some sort of unsupervised pre-training. So these are some examples, but there's lots of different unsupervised pre-training methods, right? And once you've done this kind of thing, you've got features like Dino V2 features or Sinclair features, etc. Then you can do few shot fine-tuning to new problems, right? So you've said, I'm going to collect a lot of data, which is unsupervised, pre-train my model on that, and then I'm going to collect a little bit of supervised data. And that's going to allow me to do few shot fine-tuning to problems like detection, recognition, reconstruction, and so on, right? And so the important thing to think about here is the supervision cost, right? So unsupervised data is cheap and supervised data is expensive. And so in this process, what they did is they removed a lot of the burden by sharing this unsupervised pre-training, and they didn't have to have labels for it. And you only need a few labels for few shot supervised fine-tuning, right? So computer vision did this. I think if we directly apply this to robot learning or reinforcement learning, that doesn't quite capture sequential decision-making like Amy was just saying, but it's useful to think about what an unsupervised paradigm might look like for reinforcement learning, right? So an unsupervised paradigm for reinforcement learning, one example might look something like this. So you start with training time, and you have a large corpus of unlabeled transition. So you have things like S, A, S prime pairs, but you don't have any reward labels. You're not having them be for any one particular task. They don't have to be optimal for anything, right? So let's say you went out in the world and collected some play data, or you took a bunch of failed experiments, or you got a bunch of data from sim. It's undirected, not specific to any one task, and no reward labels. Then we're going to stick it into this magical thing we're going to call an unsupervised RL algorithm. This unsupervised RL algorithm will then enable fine-tuning to a number of tasks on deployment, right? So our unsupervised RL algorithm should say that if you want to do opening of the microwave, you want to stack plates, you want to use your cutlery, for all of them, you can have a human-provided reward, but you require very, very few reward labels, right? So we want to move beyond rewards, but it's hard to specify tasks with no rewards at all. So we just want to have as few reward labels as possible, right? So the important caveat here in our problem setting is that our training data is not going to be task specific. It doesn't have to be optimal, and it doesn't have reward labels, right? So you just have a big corpus of data. And then you're going to do this magical unsupervised RL thing, which we'll try to unpack. And once you have unsupervised RL, then you say on K different deployment time tasks, you want to quickly get an optimal policy with some human provided rewards, right? And that is the expensive part. But the hope is that if unsupervised RL can take on a lot of the burden, then the fine tuning happens with minimal amounts of supervision, right? So if unsupervised RL is doing all of the heavy lifting of understanding how the world works, then you just need to like, adapt it to a particular thing you want to do. But the amount of reward labels you need is way smaller, which is really the point. Right? Does that setting make sense? Everyone with me? Okay. So unsupervised RL seems great in practice, right? Or in principle. But if I look at these data sets, I just have SA S prime pairs. No one tells me any rewards. No one tells me any policies. So what can I even expect unsupervised RL to capture, right? So if I'm not told what the tasks are, I'm not told what the rewards are, I'm not told what the policies are, what can I capture from this, this corpus? Thoughts? Dynamics, right? Like the only thing you can really capture is the dynamics of the world, right? And so one way or the other, all unsupervised RL methods capture the dynamics of the world, right? And so whether that's implicit or explicit, and that's why the title of the talk is Models Without Models, because we want to do modeling of the world at some level, right? So the first and most obvious thing you can do is let's do model-based RL, right? So I'm going to assume everyone kind of knows the premise of model-based RL, but the idea is to learn an approximate one-step model of the dynamics of the world via supervised learning, right? So you're going to say you have a data set SAS prime, or you have a data set D, you sample SAS prime from it, you do supervised learning to learn the parameters of your model P theta hat, which maximize the likelihood of S prime given S and A, right? So you just do supervised learning, plain old. And then when you're given your reward, you can do planning. You can say, I'm going to treat my model as my true environment or as my simulator. I'm going to try and optimize that reward in my simulator. I don't need to collect real samples. I can just plan in my world model or whatever you want to call it. Right? So the nice part about a paradigm like this is that it's simple. You're just doing supervised learning, right? It's easy to optimize the model because you're just doing supervised learning. And it's independent of rewards. It naturally disentangles reward and dynamics because you're literally just modeling the dynamics without any reward. And so the nice part of model-based RL is how applicable it is to these unsupervised RL settings. The problem with model-based RL is always that of compounding error, right? So you're saying that as you go longer and longer and longer in the future, you start having compounding error. And this really comes from the process of autoregressive generation, right? So you learned a one-step model, and the way you're going to plan in it is you're going to generate one step, you're going to feed it back into the model, you're going to generate one step, feed it back into the model, and so on, right? So you have autoregressive generation. And when you have autoregressive generation, let's say you made a little mistake, that'll lead to a bigger mistake, which leads to a bigger mistake, and you quickly deviate, right? So the whole field of model-based RL is kind of like trying to solve problems like this, but I wouldn't say it's quite solved. When generally, if you have a model, it doesn't just go away with more data or a bigger model. It remains kind of a fundamental problem, this compounding error thing. And so most model-based RL methods, one way or the other, have pretty short horizons, right? Which make them hard to use for our unsupervised RL problems. So we want to model the dynamics of the world, but model-based RL, garbage. We don't want to use model-based stuff, right? Okay. So the question is, how do we avoid autoregressive generation while still modeling the dynamics? So one way of doing this is saying that what if instead of modeling things step by step by step, what if we directly model cumulative long-term outcomes, right? So we model what happens many, many steps in the future rather than one step at a time, right? And so when I think of this, I think of model-free off-policy RL. I think of things like Q-learning or actor critic, right? All of them are trying to model the cumulative long-term future rather than modeling things step by step by step, right? And so let's try and cover the basics of that, and I'll get to my point in a second. So when I say model-free off-policy RL, that's of course a huge field, but I'm kind of referring to these kinds of actor critic methods which interleave the process of policy evaluation and policy improvement. Right, so policy evaluation is just saying you're going to use some procedure like dynamic programming to evaluate what the future sum of rewards are going to be in the environment. So things like our Q function. And policy improvement is going to say, let's take our Q function and use that to improve our policy, right? And so this is just vanilla actor critic algorithms. You're going to use this definition, which is going to be important, which is that of the Q function, right? So the Q function, just to recap, is the expected sum of rewards in the future, starting at a state S taking an action A, and then following the policy phi thereafter, right? And a lot of these off-policy RL methods are going to alternate between doing policy evaluation with the thing that looks like the Bellman equation and doing policy improvement to just maximize the Q function, right? And then you alternate between them. Now, the nice part about them is that if you look at this process, nowhere in here are you doing autoregressive generation, that you're not generating things and feeding them back into the model. You're completely avoiding this autoregressive generation because you're directly modeling this long-term sum of rewards in the future, right? So the Q function is directly modeling the sum of rewards in the future. So you never have this compounding error in the same way that model-based RL does, right? And so as a result, you kind of don't have this like deviation with horizon, which is why often Q learning methods work better for longer horizons. But the problem with it is that Q functions are the expected sum of rewards under a particular policy, right? So by definition, a Q function is dependent on a particular policy phi and a reward R, right? So it's the expected sum of rewards starting from a state S, taking an action A and following a policy phi. And so a Q function by definition is dependent on the reward and the policy. Yeah. So basically a Q function doesn't exist if I don't know the reward and I don't know the policy. And in unsupervised RL, we neither know rewards nor do we know policies. We just have a corpus of data, right? So model-free off-policy RL is great because it avoids this kind of compounding error, but you neither know the reward nor do you know the policy, right? So like, how am I going to use this thing, right? So it's reward dependent, it's policy dependent. So it seems crazy to use model-free off-policy RL for unsupervised RL because I don't know the rewards and I don't know the policy, right? So the premise of our talk is going to be, how do we develop off-policy RL methods that don't depend on rewards and don't depend on policies, right? And in doing so, we're going to build models without models, right? The hope is that we're going to do something that models the dynamics of the world, but do it without modeling one step, supervised learning type model-based RL. Okay, any questions before I keep moving? This setting makes sense? So we have a big corpus of data. We want to learn about the dynamics of the world. I don't want to do model-based RL. I want to do something that looks like Q learning, but I don't want to have to deal with this reward dependence and policy dependence. Yeah.
And you learn the model and then did the work.
Or planning or something. Yeah. So you like treat the model as your simulator, and then you like try to do, you can do RL in it if you want, you can do MPPI type methods in it if you want. You're just going to say, let me find the set of actions that maximize the reward. Okay? So you like hallucinate trajectories in your model, and you evaluate the reward on them, and then you try to pick the best one. There's like a bunch of variants of that, but essentially it's like doing RL or RL type things in your model. So you don't have to generate more data, just hallucinating. How am I doing on time? What's the time? Oh, wow. Okay. All right. So, okay. So there's going to be two key ideas we want to do. The first we want to do is we want to get reward independence, right? So we want to figure out how to get these models to go beyond rewards. And the second is going to be policy independence. So if I have 5 to 10 minutes, I'm going to rush through the first one and we'll really focus on the second one because that's more interesting, right? So the first idea is saying that I want to get these Q functions, but I want to get them to not depend on a particular reward. So I want to be able to evaluate new rewards quickly. And this is an idea that is not like brand new, right? So Rich Sutton and others have this idea called generalized value functions, which says that a Q function is inherently dependent on a particular reward. But you can generalize this to say, what if we, instead of modeling a Q function for a particular R, model the Q function for some vector valued function G, right? It could be arbitrary function. And so let's call our new Q function, our Q function for G, let's call it psi phi. And psi phi is just going to be the expected sum of features G, starting from a state S, taking an action A and following a policy phi, right? Exactly the same definition, you've just replaced R with G, right? So the nice part is that everything remains the same. You've just gone from scalar regression to vector regression. That's it. Now, why did I do this? It seems kind of arbitrary, right? So some folks who came up with successor features said that if your G has a particular structure, then it allows you to evaluate new rewards really quickly, right? So it says that if your G has a structure such that rewards are linear in your G, so if you can express a reward as some linear combination of the features in G, right, then you can express your Q function as a linear combination of features in psi, right? So it's just saying that if reward is linear in G, then the Q function is linear in psi. And what that does is it reduces Q evaluation for a new reward to linear regression, right? So for a new problem, I can fix this side thing unsupervised. And for a new problem, I just need to do linear regression. And if I have linear regression, then I have my Q function for a new problem, right? And so that's the idea behind successor features. It just says, I'm going to be able to evaluate new rewards just by doing linear regression. And so all that needs to hold is this linearity. And so the insight we had in this paper is like, how do we get features in which your rewards are linear? Well, you're just going to make the features random, right? And so the insight is if you have a high dimensional enough random feature, you can express rewards as approximately linear in that high dimensional random feature. And so the one-line summary is instead of modeling particular rewards, just model random stuff. And if you model random stuff, then you can quickly get new Q functions by just doing linear regression on those random features, right? I'm going to skip through the rest of it, but really the main point here is that reward transfer is kind of reduced to linear regression. Right? So for a new problem, you just get a few samples of states and rewards. You solve linear regression. The linear regression gives you your W coefficient W, and then you can get a Q function by just multiplying your psi features that are unsupervised with your W. Right? So you can just think of this as successor features with random features, right? So just saying, rather than modeling particular rewards, just model random features. And if you can model random features, you can evaluate new features just with linear regression. So the one-line insight is model Q functions of random features rather than rewards, and then transfer becomes linear regression. Right? That's it. Okay, but the second part is a little more interesting. It's saying that we've escaped rewards. We can evaluate new rewards just with linear regression. But if you look at the definition of our psi function, the psi function is inherently dependent on a policy. Right? So it's in the expected sum of features when you sum up G under a particular policy phi, right? But if I go to a new problem, the policy is different, right? So if I have, let's say, these two problems, like the policy to go here and the policy to go there are completely different. And so evaluating the Q function for the same policy for a new reward doesn't really matter because I need to change the policy as well. Right? So this is like a fundamental issue with all of these successor feature and these kinds of methods is that they depend on your policy. But if I want to transfer in an unsupervised RL sense, I need to be able to evaluate new policies and new rewards. Okay? And so the problem is we have unsupervised RL. I just got a corpus of things. I can do this psi-phi thing with some random features, but I need to know pi. And if I don't know pi, then I don't know what to evaluate, right? And so the issue is we don't know what policy to evaluate. So how do I do unsupervised RL? Right? I can't even define a Q function without a policy. Doesn't make sense. So how are we going to eliminate policy dependence? Well, we're going to do the most obvious thing. If I don't know what policy to evaluate, I'm just going to model all the policies, right? And so it's going to say that rather than modeling a single policy, I'm just going to model a distribution over all possible outcomes. Right? So let's say a particular outcome, a sum of features in your environment, let's call it psi. If I don't know what policy to evaluate under, I'm just going to say, let me model the P of psi given S for all possible policies, right? And so let's say we had a simple environment. It's a four-state environment, right? S0, S1, S2, S3. And those G's are the features, right? Normally what's going to happen is you're going to say your value function is going to have a scalar for a particular state. So S0 will have some psi, S1 will have some psi, Sn will have some psi, right? And what we're going to say instead is let's model a distribution over size, right? So this is going to say what is the cumulative features under a particular policy. This is going to say what is the cumulative features under the distribution of all possible policies that are contained in your data set, right? And so the difference here is that I don't know, it's basically a lesson in not committing, right? It's saying that I don't want to commit to a particular policy. I'm just going to model the distribution over all possible policies. And so you can think of this P of psi given S kind of like an affordance model. It tells us what is the distribution of our outcomes in the future from some particular state, considering all policies in my data set and my dynamics of my environment. Yeah. So let's kind of go through an example that'll help us understand this a bit better. Okay, so if psi corresponds to a single cumulative outcome in the environment, so P of psi given S is the distribution of our outcomes that could happen in the environment. Let's ground it in this example. Okay. So the two outcomes from state S0 are going to be S0, S1, S3, and S0, S2, S3. Right? And so S0, S1, S3, what is the cumulative G's? What are the cumulative G's going to be? What is the cumulative outcome going to be? G's. This addition.
2, 1.
2, 1, right? So path 1 is going to be 2, 1. And similarly, path 2 is going to be 1, 2, right? You're going to have 0, 0, plus 1, 0, plus 1, 1. You're going to have 2, 1, 0, 0, 0, 1, 1, 1. It's going to be 1, 2, right? And so you're going to have two different paths. And so you're going to have a bimodal distribution. We'll have one mode at 1, 2, and another mode at 2, 1. And so the point here is that you've not committed to any one of these policies. You've said the two possible outcomes in the world are 1, 2, and 2, 1. Right? And the nice part about doing this is you're in the unsupervised RL setting. You've modeled all of the things that can happen. Now, when someone tells you what the reward is, what do you want to do? You can pick the mode that's the best, and then just try to take the actions that accomplish that, right? And so, does that kind of make sense? Like, yeah. Yeah, so it can be a pretty multimodal distribution. And so one of the challenges here is you have to represent exponential number of modes in your like multimodal distribution, but we use something like a diffusion model for P of psi given S, and the hope is that is pretty expressive. But yeah, I think the challenge here is you're doing a lot of the test time planning at training time. And so you like incur all of the complexity of planning at training time. And so that goes into your function approximate. Good point. Okay, so the point is we didn't know what policy to do, so we're just going to model all the possible outcomes in the world. How do we do that? Well, I'm going to skip this, but you can think of it as kind of like a distributional Bellman equation. It's like essentially the same thing as the distributional Bellman equation, but on the behavior policy. And so intuitively, you can kind of think of the thing like this. Let's say the distributional outcome was 1, 2, and 2, 1, but they were unimodal because there was only one outcome from both of these. And you can kind of combine them into a bimodal distribution by just doing dynamic programming, right? And so you can kind of think of it as propagating distributions backwards. So don't worry about it too much. Just kind of feel out the vibes. But the important part here is once we have P of psi given S, like that doesn't tell me how to act in the world, right? I need to act in the world. And so what you need is a way to say, if I want to accomplish this outcome psi, how do I get an action A to accomplish it, right? And so a simple way to do this is something like an inverse model, if you all are familiar. It's basically saying, let's try to train policy pi of A given S in psi, which takes in a desired outcome and produces the necessary action to accomplish it, right? And so you can just train this with supervised learning. The important part here is that once you pick an optimal psi from P of psi given S, you can run it through your policy that gives you an action to take in the world, and you can act in the world, right? And so the point is, once my reward tells me what psi is good, what psi I should pick, I take that psi, I stick it through my policy, the policy gives me an action and I'm good, right? In some ways, you can think of this like goal conditioned RL, but not just on goals, it's on all possible outcomes in the environment. Okay, so let's kind of run through a quick example, super quick to like ground the intuition. It's saying that in this kind of example, the P of psi given S is going to be a bimodal distribution at 2, 1, 1, 2. And the inverse model is going to say, let's say I wanted to accomplish 1, 2 at the first state, right? To get to 1, 2, I'm going to take the bottom path. And so the policy is going to produce A1. To get to 2, 1, I'm going to take the top path. So the policy is going to produce A1, right? And so the nice part is that you can train this whole thing unsupervised. And there's no mention of a policy, like no mention of a policy in a Q function anywhere. It's kind of like you're modeling the distribution over all possible things in the world, right? So it's completely unsupervised. So the important part here is rather than modeling the outcome for a particular policy, you're modeling the distribution of cumulative outcomes for all policies that are contained in your data set. And this allows you to avoid committing to any one policy. So you can represent all policies, which can represent all possible reward functions that you might want to optimize later that are Markovian. Right? So you want to model all the policies. That's it. Okay. So what do we want to do with this? Well, we really want to use this for transfer, right? So the point is we have an unsupervised corpus of data. We did all this fancy stuff that I just talked about. It gives us this P of psi given S and a pi of A given S psi. But I don't care about unsupervised learning. I care about doing things in the world, right? And so how do I use it for transfer? How do I use it for new problems, right? So if I want to use it for new problems, I'm going to follow a really simple procedure. I'm just going to start by doing linear regression. So I'm going to say I'm going to get a set of states and rewards, S comma R. I'm going to solve linear regression to get that W coefficient we're talking about, right? So it's just saying, what is the linear function? What is the linear weight on the features G that will give me my reward? And then I'm just going to solve a really simple optimization. It's going to say that if psi given s tells me all of the possible outcomes in the world, right? Tells me all of the different things that I could do. I choose the one that has the highest reward, right? So W times psi, as we talked about at the start, gives me my value function. I'm just going to pick the thing that is doable in the world, but has the highest value, right? So you can think of this as saying, these are all the possible outcomes, pick the best one. And so you're going to find the thing that has the best outcome, stick it into your policy, run an action, and repeat, right? And so the point is that you solve this optimization, you can solve any number of ways. Random sampling, convex optimization, gradient descent, whatever you want. And it gives you an action, you execute the action, you re-query your model, just like replanning, like MPC, right? And so the point is we've done unsupervised RL, but we've not used model-based RL anywhere. We've used model-free RL everywhere. But we've just done it by modeling a distribution over possible outcomes. What's really nice is when PF psi given s is a diffusion policy, this planning procedure is just guided diffusion, which means you're going to run like Lundgren dynamics for a diffusion model and just add this weight to it. That's it, right? So that makes it really easy and nice. Okay, so what's the point here? We've done these generalized occupancy models. It allows you to directly model these cumulative outcomes because it's using off-policy TD learning. You never do autoregressive generation, so you avoid compounding error. You don't commit to a reward because you're just modeling random features. And you don't commit to a policy because you're modeling all the policies, right? And so in a way, you're taking the structure of an off-policy RL algorithm and just making it applicable in the same way that a model-based RL algorithm is, right? It's a little bit complicated, but the point is that now we don't need any models. We just need to use these generalized occupancy models. Okay, there's a number of plots with our numbers better than other numbers. I wouldn't show them to you otherwise. I think some things that are cool is that you don't have to commit to just solving tasks that are goal conditioned. You can solve tasks that are specified by arbitrary Markovian rewards. So for instance, preference-based rewards or rewards that draw a UWCS kind of, right? And it allows you to retain the benefits of policy RL, like stitching and so on. But the main points I want to get to is that unsupervised RL is really about modeling the world. There are many ways to model the world. Some are better than others. Model-based RL is arguably the worst way to do it. And so more generally as a community, I think we need to think about ways to do modeling without modeling. This is just one example. But I want to encourage you all to think about how we can do model-based RL without literally modeling one-step dynamics. These GOMs are one class of doing this. And these are all the people who did the work. So thank you.
Time for questions.
So in your talk, like you said, you will generate all policies from the policy class. But when you have offline data set, you wouldn't want to generate like policies which explore outside the data set. So once you do that, you learn something which is probably not applicable for the one of the modes of your distribution.
So you're not doing it for all policies, you're doing it for all policies that are in the coverage of your data set.
So how do you sample those?
So you don't have to explicitly do it. And so the way that I kind of skipped that part a little bit, but it's this distributional Bellman equation that you have. And so the distributional Bellman equation tries to say that you like, if your distributional outcomes now is going to be the distributional outcome, so like outcome now plus a sample from the future. You sample from your behavior policy. That'll give you the choice. Yeah. So like all paths more than all policies. Yeah. Yeah.
Yeah, so saying we should never do model-based RL is the worst thing. It seems a little bit like a strong statement.
Yeah, it's a
I
strong
see where it comes from. Right? Like compounding error is a big problem.
It's a strong statement.
But staying, it seems like you're really focusing on this idea of that sort of compounding error being a problem. And if we're gonna have compounding error, then we can't chain these one-step models. So why not just do model-based things like long-term options? Does that have some sort of the same benefits?
I think that's way better than doing model-based RL in one step. So like doing things like closed loop modeling. So like rather than modeling open loop actions like we often do, you can model options. I think that's significantly better. I think it's like, I was mostly just doing it as hyperbole. But I think in terms of I think there's actually a really interesting question of when we should, I think the question of when we should use models versus not, perhaps the question of when is a model simpler than a policy or a Q function? And like certain problems, like you're in a maze and you want to feel your way out, like the policy is potentially simpler than the model. And other problems, the model is simpler than the policy. And I think that's perhaps the more pertinent question, rather than like always doing models versus always doing policies. But I think that either way, doing one-step open loop models is going to be bad, especially for robotics problems. It just doesn't scale with Horizon. Modeling options is certainly way better.
All right, I guess, thank you again. So after this, we're gonna have a coffee break until, 3 o'clock. Yeah, 3 o'clock. So be sure to be back. It'll be a short coffee break. So